Hello, everyone. Today we're going through a problem. It's an interesting counting problem, so let's get started really quick. So the problem is how many five-digit positive integers exist where the digits are non-increasing from left to right. So, for example, 87,400, no, 87,743 and 10,000 satisfy those conditions, but 7,897 and 33,429 don't. So what we're going to do is we're going to generalize this five-digit number. Right. I'm going to call this five-digit number A, B, C, D, E. Right? Your digits are A, B, C, D, and E, and they come together to form a five-digit number. Now, by non-increasing, right, they mean that essentially A has to be greater than or equal to B, which has to be greater than or equal to C, which has to be greater than or equal to D, which has to be greater than or equal to D, E. Now, notice in order to cover all possible cases, we're going to have to pick and choose where this inequality is strictly greater than and where it's going to be lesser equal to. So we're going to have to shuffle between strict and non-strict definitions of the inequality. Because a subset of this inequality could be like, oh, A is greater than B, is greater than C, is greater than D, is greater than E, right? Now, if A is greater than B, is greater than C, is greater than D, is greater than E, well, that means you have five unique digits. But for example, if A is greater than B is equal to C, is greater than D, is greater than E, then you only have four unique digits, right? So it looks like, based on this little exploration that we've done here for the condition, that we can organize our problem based on casework. So let's get started with that. So we're going to divide this problem into cases based on the number of unique digits the number has. So case one, we have five unique digits. All right. So if we have five unique digits, and remember, we have our, I'm going to write our five-digit number down. And if it's five unique digits, then A is greater than B, is greater than C, is greater than D, is greater than E. We have 10 digits from 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we have to choose five of these, right? So we have 10 choose five ways to choose five digits from the 10 that we know we can select from. And out of those 10 choose five combinations, there's only one such combination, right? Such that the set of five digits that we selected is ordered from greatest to least for our case. So we've established a one-to-one correspondence, right? I'm gonna write it out. One-to-one correspondence between number of ways to choose five digits and the number of ordered digits A, B, C, D, E, such that A is greater than B, is greater than C, is greater than D, is greater than E. So that means that there are, that there are 252, or 10 choose 5. 10 choose 5 is just 252, which is, we can calculate it manually. 10 times 8 times 9 times 7 times 6, divided by 120. So this cancels, this cancels, this cancels. This cancels, we're left with a 4 up top, which is just 28 times 9, this is 252. So that's how many cases we have for our first case. All right, and now we move on to our second case. We have four unique digits. Okay, there we go. So in our second case, we have four unique digits. Like I said, now instead of selecting five digits, we're going to be selecting four because we only need four unique digits. So we're going to start with 10 choose 4, right? And let's say our digits are A, B, C, and D. Well, we know one of these digits have to be repeated. Now that digit can be A, that digit can be B, that digit can be C, or that digit can be D. And keep in mind, A is greater than B, greater than D, right? So we have 10 choose 4 ways to select four digits, right, from the 10 that we were given. But for each of those 10 choose 4 ways, there's four ways to repeat one digit, right? We can repeat the first digit, the second digit, the third digit, or the fourth digit. So in reality, we have 10 choose 4 times 4 different five digit numbers whose digits are in non-increasing order from left to right. and have 4 unique digits. So in this case, let's calculate 10 choose 4, 10 times 9 times 7 divided by 24. So it's going to be a 3. So 10 choose 4, right, is 210. Now we have to multiply this by 4 to get the number of cases that we have. And this is just equal to 840 for this case. All right, and we move on. Case 3. We have 3 unique digits. Right? So we know there's 10 choose 3 ways. Let me calculate it beforehand. There's 10 choose 3 ways to, what do you call it? To select 3 digits from the 10 that we're given. Say those digits are A, B, and C. Now, in what combinations can we repeat these digits such that we get a 5-digit number, and that's a non-decreasing order? And here we're just assuming that like A is bigger than or equal to B is bigger than or equal to C. It's fine, right? Or strictly. Because if we keep it a non-strict inequality, will overlap with other cases in the problem. So let's keep this a strict inequality. Okay? Alright, so how can we do that? Well, if we're given 3 unique digits, and we want to use those 3 digits to make a 5-digit number, we can repeat one digit 3 times, like this. So A, B, C, A, B, 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 C, or A, B, C, C, C. So these are all the ways that you can repeat one digit 3 times and make a 5-digit number. That satisfies our conditions. And then another way is to repeat 2 of the digits. So like, I could repeat A and B, I could repeat A and C, or I could repeat B and C, like that. And in total, there's 6 different ways we can make a 5-digit number that's non-increasing given 3 unique digits. So for each of these 10 choose 3 ways that we can get a set of 3 digits and order them from greatest to least, right? There's 6 separate ways where we can make a 5-digit number that satisfies the conditions. So there's 120 times 6, which is 720 ways that satisfy our conditions for the problem in this case, right? And let's move on to case 4. We have 2 unique digits. All right, like I said, let's first start by counting the number of ways we can pick 2 unique digits and order them. That's 10 choose 2, which is 10 times 9 divided by 2. And that's 45, right? Say our unique digits are A and B. Now, how can we make a 5-digit number from these? Well, we can repeat one digit 4 times, right? We can have A, B, or A, B, 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 B. And we can repeat one digit 2 times and then the other digit 3 times. So we can have A, B, B, B. Or we can have A, B, B. Like that. And those are our 4 ways of making a 5-digit number that satisfies our conditions if we're given 2 unique digits. So we have, in this case, 45 times 4 equals 180 ways to solve this for this case. All right, and then our last case, we have 1 unique digit, right? If we have 1 unique digit, we can't have 0 because we can't have a 5-digit number that starts with 0. So any of our unique digits can be from 1 through 9. And for each digit, there's only one way to make a 5-digit number, using only that digit. So there's just 9 ways in this case. All right? So now all that's left is to tally up the results and add them up to get a final answer. So for our first case, it was 252. For our second case, I believe it was 840. Let me check. Go back up. Yeah, it was 840. For our third case, it was 720. For our fourth case, it was 180. And for our last case, it was just 9. Let me make sure. 189. Yep. Now, we just got to add these up. Okay. 2 plus 9 is 11. Carry the 1. 1 plus 5 is 6. 2 plus 4 is 10. 10. 2 plus 2 is 12. 18, 20. Right. 2 plus 2 is 4. 8. So 4 plus 8 is 12. 12 plus 7, 19. And equals 120. So we get a total of 2,001 numbers that satisfy the conditions for this problem. Well, guys, I hope you found this explanation helpful, and if you have any questions, feel free to reach out. Thank you.